The class of today is on fragile regions in the human genome. And we are going to use it as an example of combinatorial algorithms. I wish to ensure that the transmission is proceeding correctly. Yes, it is. And so we go to the next slide. What is bioinformatics? Bioinformatics is like to transform a man in a mouse. And we are going to see what does it mean, this weird statement later. The point is that man and mice have DNA, but their DNA is ordered in a different way. That is the main point. It is like a book. We have the same book, but the page order is different. In this case, what it shows is that in the mouse and in the human, for example, this green arrow in the mouse is right to the left and is the 1, 2, 3 page number 4, while in the human is the second last one. But the point is that in these cases, anyway, we found similarities and we identify huge similarities between the mouse and the human genome. And we identify these similarities using the previous, to call techniques that we learned in the previous chapter. Now, we wish to transform a mouse into a man. The chromosome is the same, but the ordering is different. We start in this way. At this point, we swap this block in the opposite direction. We do the same with this block, the red one, the fifth block from the left. And in this case, we are going to swap not one, but 2 blocks. The fifth and the fourth block from the right, and I'm going to swap them and change direction. Every time I reverse, I change direction. This is even a biggest change in direction. I'm going to put the last block as the first one reversed, the second last and second one reversed, the third last as third one reversed, and go forward. And now I have a human. The ordering is the ordering of the blocks in humans. Now, what we are going to speak about are rare events called evolutionary earthquakes. And this is what we described before. Not every day we have these kind of events. And the question is, are they random or are they, are they randomly distributed in the genome, or they have specific hotspots? This is an example. 1, 2, 3, 1, 2, 3, 4, okay, of a chromosome of a prokaryote. And I wish to understand if do we have any place in which it is more common to get an arrangement. We are going to repeat the previous slide. We have an earthquake at this point. We have another earthquake at this point. The earthquake changed direction. Here we have an earthquake that changed direction not of 1, but of 2. -11 and -3 are going to change, swapped and changed. Here I have an even bigger earthquake between -10 and -11, I think. And I'm going to swap all. And this is identified as rearrangement hotspot. The problem is how much of this is real and how much is not. Identify in this way locations in which is more likely to have rearrangement. The problem is what we call the random breakage model. We have a random breakage model of chromosome evolution that I described before. And the hypothesis is that in reality, we do not have places where it's easier to get a chromosomal rearrangement. But what we could do is to assess the random breakage model and to check if our prediction fits what we observe in real genomes. What is the predictive power? This is a method called the Monte Carlo method. We are going to apply a random reversal to a chromosome consisting of M genes. Can we predict how many blocks of length K will be generated? So we apply a random reversal to a chromosome consisting of M genes. Can we predict how many blocks of length K will be generated? This is a frequency distribution by block size. And we are going to compare this histogram of the simulated data with the real one. We are going to remember that the synteny blocks are groups of connected genes. In the 90s, this theory was well accepted by biologists.